Today we're going to talk about parameterization of surface fluxes. Last time we talked about subgrid scale fluxes, those fluxes that are not resolved by our grids, and they are important to represent because transport of quantities, momentum, temperature, and other scalar quantities is done not only by resolved velocity field, by field that is resolved by our grid, but also by fluid field or motion field that is not represented by our grid, so-called subgrid scale motions. And in certain conditions that we actually considered, like if our grid scale is within the so-called inertial subrange of turbulence, then we could analytically derive very useful expressions for fluxes, for eddy diffusivities, and other concepts using Kolmogorov theory of turbulence. Now, all this, what we've talked about in the last lecture, is concerns fluxes that are well within the fluid, away from surfaces. Why it's important? Because near the surfaces, character of turbulence changes. First of all, the eddies cannot be very large near the surface because, well, surface kind of restrict them. And also, right near the surface, there is, of course, you cannot ignore effect of viscosity anymore. Very close to the surface, viscosity is apparent. And all our kind of theory of inertial subrange of turbulence, when we assume that turbulence is isotropic, so it's the same, statistically the same in all directions, and dissipation only happens in a very small scales and so on. And there is this cascade of turbulence from large eddies to small eddies and so on. It is kind of not very valid right near the surface, because near the surface you actually have like some obstacles, some maybe, like in the case of atmosphere, you can have houses, you can have trees, you have grass, you can water surface, and all those have very different effect of turbulence. Obviously, like if it's city, you would expect much stronger effect of surface on the interior of your flow. If it's ocean, like or lake, it's completely different effect on say momentum fluxes and so on. And also there is exchange of heat and momentum that depends on properties of the surface. So how we would account for all this? Our grid size can be, even in large eddy simulation, is typical like tenths of meters. This is your grid spacing, and all these obstacles can be much smaller than that, or maybe bigger than that, like in case of city. So, but that's different story. But let's say that those obstacles are not resolved by our grid, so all this generation of turbulence by the surface is not resolved, and we cannot use our formal Kolmogorov theory in this case, by the reasons that I already mentioned. So, how you parameterize all these fluxes of momentum, like U prime, W prime, these Reynolds stresses at the surface, or fluxes, say, of potential temperature or heat fluxes at the surface. So how you parameterize them? And for that, we will use so-called Monin-Obukhov similarity theory, which is kind of standard for this kind of problems in our field. Let's first start from some simple case, so-called neutrally stratified surface layer. So there is no heat flux. In this case, things are a little bit simpler. First of all, what is surface layer? Surface layer, by definition, is a layer where all fluxes, vertical fluxes of heat or momentum, are constant with height, don't depend on height. So surface layer is these fluxes like momentum flux, for example, or horizontal component of velocity, vertical averaged in time, or heat flux, they constant. Because it means that there is no divergence, vertical divergence of those fluxes in surface layer. So basically we assume that our surface layer is a layer where you can ignore this divergence, and only the whole purpose of this surface layer is to transport momentum or heat through that layer without actually accumulating it in that layer or taking it from that layer. So it's basically just this layer just conducts these quantities through it from the surface to the free atmosphere. So it's a layer where this exchange happens. So our grid generally should be put, our lowest level of the grid is usually put not on the surface itself, because surface is not actually well defined, especially if you have all these features on the surface, but somewhere above it. So this is our grid, first level. So it's k equals 1 level, and k is increasing upward. So this layer is, we put our first level within the surface layer, not at the top of it, but somewhere within. So this surface layer, typically estimate of that would be like, this is maybe about maybe typically 50 meters. 50 meters above the kind of some average surface height. So this is our surface layer. Now how we find those fluxes? For that, let's first ask ourselves a question. So there is this very strong gradient of wind, obviously, because right at the surface, your wind should disappear because of viscosity. Your wind is 0 right at the surface. This is a so-called no-slip condition. So you have some velocity wind profile, right? Like so that at the surface it becomes 0, and then it very quickly increases, so let's say, with height. So there is some flux of momentum, of course, because here there is friction here, and your velocity is increasing with height, but so momentum flux, say horizontal momentum, so it's vertical flux of horizontal velocity is actually negative here. So your momentum is actually going to the surface where it gets destroyed. So what is this profile? Let's first ask this question. What is du dz equals to? And what it depends on. So at each height in a surface layer. Again, I repeat that this is surface layer. So in surface layer, the flux is constant. So it's negative and it's constant. So so u prime, w prime, this flux is constant, and it is it will be our independent parameter. So it's given. Let's say that flux is given, and we're trying to find wind profile, like here, so or gradient of wind profile, vertical gradient. So it's constant, and it's this constant is usually called u star square. So because by dimensionality, dimensions of this flux are as meters per second times meters per second, so it's meters square per second square. So this is some velocity squared. So that's why it's called, we just denote it by u star square. And this is u star is called friction velocity. So it's given. What else is given? Well, height, right? So this is another independent parameter, height. So it's also given. And what else is given? Well, maybe some characteristic of the surface, how rough it is, because you know it should depend on that. But because we're already given flux, we kind of, it's implied in that flux how rough the surface is. So that's not actually the parameters that we use right now here. So we have only basically two parameters, nothing else. And what we need to find is this guy. So we can formally write it like this, that d u dz is some function of our parameters, like u star and z. How we can find this function? Of course, we can go to the field and find some relatively uniform surface and start measuring all this stuff, like u star, like using, say, turbulent perturbations and computing this correlation between vertical velocity and horizontal velocity. So we measure perturbations of horizontal velocity and vertical velocity, compute this flux, so it's independently measured. So you compute u star, you measure u star, then you know your height, and you change them, and then you create this kind of formula that will say that it's in u star and some power b times z in some power c times some other constant. So this is what normally sometimes people do, instead of just first thinking about the problem. But can we actually find this function without actually going to the field, just by thinking? And this is actually, it's possible in this case, because the problem is very simple. It's only two parameters, very simple parameters. Now let's think about dimensions of this thing. This thing has dimensions, velocity over a length, so it's meters per second over meters, so it's dimensions are seconds, inverse seconds. So dimensions of u star are meters per second, and dimensions of z are meters. So let's say that there is this function, I don't know, maybe cosine of u star times z of some power. So we don't know this function, but it's some function. What if we establish that function, let's say that there is a function. How do we know that this function is true? Well, the laws of nature should not depend on measurements, on units of measurements that you use. For example, if you use in meters something, why not use inches? You can measure it in inches, or you can use it measure in centimeters, or whatever, or millimeters, or in the sizes of proton if you want. So, and each time when you change units, your value is changing. If you measure in meters per second, velocity in meters per second, and start measuring in inches per hour, of course the value of that, the same velocity, will change. And so function should also change then, right? But let's see that we switch from meters to inches. So this function value will change, because there are some values of this quantity here that depend both on meter, and there is some functional formula, and of course values will change and function will change. But this guy should not change because it doesn't have any meters in here. Which means that this function should not be just function of u star and z, but it should be a function of u star divided by z. In that case, the units of this quantity are seconds, or inverse seconds. So it's the same units as this guy. So now, if we change from meters to inches to centimeters, nothing will change. This function is not going to change. But the problem is that this function should not also change if we change units of time. So instead of seconds, we change them to hour or to minutes. So du dz value of that will change. And this function also will change, but they should change in tandem together, so that this equal sign does not change. How you accomplish that? The only way of doing so is just that we actually, because units are the same, we conclude that this function equals some constant times u star over z. It's linear function. Because otherwise, so if you change now this quantity proportionally, depending on if you switch units, it will change the same way. So, and nothing will change. From that, we actually deduce that this must be true. So you see, we immediately, just looking at dimensions, we immediately came up with functional form of this function without actually doing any measurements. It just units should be, this is the true power of dimensional analysis. The laws of nature should not change depending on your units of measurements, which yardstick you use. So from that, you immediately get this, that the z over u star du dz must be constant. And this constant alpha, which I noted here, alpha equals to, just for some reasons that are going to be known later, it's equals to some constant 1 over kappa. It is constant, and this kappa is called von Karman constant, and it's equal to about approximately 0.4. And you find the 0.4 from experiment, because this law of nature does not change on a specific case that you're looking at. It should be just some surface layer such that your fluxes are relatively constant with height, and it should be neutrally stratified and should be statistically kind of steady. So it's not like something like really changing much. And also your results should not depend on a horizontal scale, because there is no parameter here, x. So it should be horizontally uniform. So as long as those conditions are met, this law should be a universal law. And for universal law, you have this universal constant kappa that you can measure in laboratory for one particular case. And as long as you measure it for one particular case, it's true. This law is true for all other cases where your assumptions are met. So great. So now we have this law that we found just by theoretical consideration without any experiment. So now we can now write our flux u star. It's equals, remember, minus u prime w prime. So it's equals to z kappa du dz. So now sorry, this is u prime square. So it's actually you multiply by 1 du dz. So this is flux equal to this, and remember we introduced last time, we introduced so-called eddy or turbulence, eddy diffusivity. So which is was like a k this turbulent du dz, from which we conclude that actually our k, this diffusion coefficient, turbulent diffusion coefficient in the surface layer, is actually proportional to height. So kt equals to kappa z u star. So now by units, this is it has units, of course, of length. So this is some kind of mixing length, L. So this is equal to L times u star. And this L mixing length so L equals to kappa z. So you see that your mixing length is directly proportional to height. So basically, this is a physical interpretation of that is that your edges become bigger and bigger and bigger away from the surface, kind of proportionally bigger to the distance from the surface, and your transport kind of increases. I mean, your length over which stuff is mixing is actually increasing as you go away from the surface. So this formula actually was first found by Prandtl in laboratory experimentally. So he just found, and he basically, this is called Prandtl hypothesis, that eddy diffusivity is proportional to mixing length and U star and friction velocity. And mixing length is a linear function of height. Prandtl actually made this hypothesis, and we actually see that it's just consequence of this dimensional analysis argument. It's not, you don't really need to propose this. You can just basically first just look at dimensions of things to find out that this must be true. So now you can, it is difficult to use this formula well, how you use it in a model, because what you need is basically just flux given velocity at some height at your first level of grid. So this height is z equal to h. This is your height is given. This is your model first level height above the surface. And also what you're given here is velocity at that height, u at height h. You're given that in your model, by your model. So now you need to compute flux to compute help to compute u or velocity at the next time step when you compute this diffusion in the vertical in your momentum equations. So, so we need to, this formula is hard to use because what it describes is just this profile in here, but you need some velocity at h. So from that you see that you need to integrate it. So let's integrate it, this formula. So you have du integral dz equals to kappa u star, kappa u star divided by kappa z. So it's u star divided by kappa integral of dz. This one is, of course, incorrect. It's du dz over z. So now, what's the integral? What's the limits of integration? Is it from like 0? Let's say that this is 0 to h. But actually, that wouldn't be the case. That would be not plausible because integral from 0 with it's, well, let's integrate it first. So we have this one is just u, and we assume that u is actually becomes 0 as somewhere at the surface. So this one is just equal uh. So this one upper integral is definitely h, but here is, we don't know. So we have u at h minus u at this, we don't know, equals to u star over kappa logarithm z over, we don't know. So now if z equal to 0, if we, is this question mark is 0, obviously you have a problem. So this one is infinity, and log becomes undefined, and you have problems. So we actually choose such such height at the surface and call it z naught, that this u at z naught becomes 0. So z naught is some hypothetical height where velocity becomes zero, but it's not real height. I mean, actual height where velocity gets to zero, because it happens very close to the surface where all our assumptions basically break, and there is molecular viscosity there and all these characteristics of roughness that we cannot account for this theory. So basically we say, okay, we cannot do that. We just call this hypothetical height where velocity kind of asymptotically becomes zero, but not in reality. Asymptotically becomes zero, and this height is z naught. So this is basically incomplete theory in this regard, but we basically sweep all these kind of details about the surface into one parameter that we call z naught. And then, of course, we have a problem how you obtain z naught. So this is our formula that we can, from that, we have u star equals to kappa divided by log z, well, this one z is actually not z, sorry, it's h. Log of h divided by z naught times u at h. And so our flux minus u prime w prime equals to this guy squared equals to kappa square u of h squared divided by log h over z naught. So you see, we now can use this formula in our model, right? Because we know u at h, this is our lowest grid level, and we know h, and we need to know z naught. And so how to obtain z naught? So this is called, z naught is called, is roughness length. And well, roughness lengths generally can be obtained only experimentally. So for various surface types, let's say you have forest of certain height, you have pasture, you have some farm field, you have bare soil, you have like some suburban area, let's say. So you just basically need to experimentally find some typical values for that z naught. And typical rule of thumb usually, so it's the rule of thumb. So this is not actually exact, but it's kind of gives you idea. So rule of thumb is that z naught is about 10% or 0.1 of hc, where hc is a typical obstacle height. So let's say that if it's like, say, suburban area with typical kind of a house height, I don't know, maybe 5 meters or so, and trees around, so it's typical kind of maybe 5 meters. So then HC is something like 50 centimeters or so. And over, say, grassland, the typical height of grass is, say, I don't know, 30 centimeters or so, like that. So typical roughness length is something like maybe, I don't know, 3 centimeters or 0.03 meter, or so, and so on. So there are like, you can, this is basically parameters that you input to the model as your kind of data, external data that you need to tabulate, or like different, say, surface types in your model may have different z naught. But as long as you know z naught, you know your grid level height, say 50 meters, you put your highest, your lowest grid level at 50 meters, and you know the velocity there, result velocity, you can compute flux and use it in your computations. of in prognostic equation for momentum. So now there is some case, one case when a different formula is used for z naught. Actually z naught can be computed, and that case is a sea surface. So when you have water surface, lake or sea, and there is some wind over it, of course wind generates waves. And the height of waves should depend on wind, right? So when you have strong wind, it's more kind of rough sea, the seas are rougher. So there is some correspondence between wind, so this friction velocity, and roughness length of the sea surface. And again, using this dimensional analysis arguments, it should all this roughness length over the water should depend on two things. One is u star, obviously, this friction velocity, and also on gravity, like, because waves are actually driven by gravity. So if it's like, say, Jupiter, a lake on Jupiter, and it's very strong gravity, you definitely need more stronger wind to generate the same waves as on Earth, at the same height. And so using the same dimensional analysis argument that we did for this formula, you can actually deduce that z naught over like sea surface, z naught should be related with the following dimensionless parameter, z naught times g gravity divided by u star square. Then this thing is dimensionless and it's constant. And this constant, like c, is called Charnock formula. So Charnock constant. So this formula is called Charnock formula. And this alpha equals to something like, from observation, so 0.016. And then you can compute your z naught that you use in this formula. So generally, so now we're done with momentum for neutral conditions. So we have this momentum flux when there are no surface fluxes or heat or anything like that. So in that case, we can use just this formula, which is called bulk aerodynamic formula. So basically, bulk aerodynamic dynamic drag formula, so that your flux of momentum equals to some drag coefficient, so for neutral conditions, so CDN, so it's drag coefficient. CDN times U at level H squared. So this is simple drag, aerodynamic drag formula from this. And from that you see that for neutral condition, this one is very easy found as kappa squared divided by log H divided by Z naught squared. Here is squared, so certainly, yeah, always make these little mistakes. So, done, right? No, it's we're not done yet, because now we need to talk about other cases, because we need also fluxes of heat from the surface, fluxes of water vapor from the surface, and other scalars, if we have them. And also we know that in different conditions, if it's stable atmosphere, or if you have heat flux from the surface, it's heated. If it's positive, it can be different drag than if you have, say, negative flux or cooling flux. So we need to extend the theory to the cases when we have surface heat fluxes, and that we're going to do next. Let us now generalize our theory to the case when we have surface heating. Obviously, if you have a heated surface, your turbulence level will be different, and it would definitely affect the surface layer behavior. Transport of fluxes will be transport of various quantities like momentum and temperature and other things like water vapor will be different depending on your surface heat flux. More precisely, it should be surface buoyancy flux, because turbulence is driven not only by perturbations of temperature but also by perturbation of water vapor. More moist air is more buoyant for the same temperature, and we take that into account in thermodynamics by virtual temperature and correspondingly virtual potential temperature. You know that, I hope you know that from your elementary atmospheric physics class. So we have additional parameters such as, so before we had only U star and Z. Now we have another independent parameter that is surface buoyancy flux, or W prime theta V prime. And that, buoyancy involves not only perturbations of potential temperature, for example, but also it depends on gravity acceleration. Obviously, if you have very strong gravity, it's one thing. Other gravity, like weaker gravity, is a different thing. So it should be multiplied by like buoyancy. Remember from one of our classes, it's G theta V prime divided by theta, some reference temperature. And so it can be also written like just beta theta V prime, where beta is just gravity that always comes divided by some temperature scale. So it also should depend on beta. So we have two additional parameters that we need to account for, and this theory that generalize the surface layer theory to this case of stratified surface layer is called Monin-Obukhov similarity theory, or just Monin-Obukhov theory. So according to this theory, as we wrote before, that this dimensionless profile of momentum, so kappa z divided by u star du dz. For neutral case, it's equals to 1. That's why we define this constant as 1 over kappa, so that we put kappa in here. But it's now a general function for momentum, like that's why we put the Fm of some dimensional parameter that actually takes into account this buoyancy flux at the surface. So it's called, let's write it as the following: Z over L, because this one is dimensionless, it should be a function of dimensionless parameters. Then you can change your units of measuring velocity analysis, nothing will change. So that's why it should be in this form. And L is defined as, just historically defined this following way: it's minus u star cubed divided by kappa, beta, and buoyancy flux. And it's called Monin-Obukhov length scale. So we can write similar formulas for, we assume that there is similarity law for temperature and for water vapor, so we can also write it like the following: theta z divided by theta star d theta v dz equals to f h. And this function should be different than for momentum for various reasons, but it's also kind of dimensionless function of z over L. Those two functions are called universal functions. And they cannot be obtained from theory, they should be obtained from observation. So they're empirical, and you just basically need to do some field campaign or do some laboratory setup to obtain those functions. Okay, so and similar, now I introduce here theta star. What's theta star? Theta star is defined as the surface flux equals to u star times theta star. And similarly, we can define the evaporation flux at the surface as u star q star. So, and then write similar to water vapor. And water vapor behaves, we assume, similarly to temperature, so we use the same similarity function here, or universal function. So this is formally kind of formulas that we start from. Now, similar we did when we derived bulk aerodynamic formula, we need to integrate these expressions, and that's why this universal function usually there are many several types of those functions, come from different kind of researchers, and generally the biggest requirement that this function should be easily integratable analytically, because that's otherwise we cannot find the so-called bulk formula. So they do this empirical fitting and then find a function that fits through this data that they obtain in laboratory or in field campaign that can be integrated analytically. And so we assume that they integrated, and now when we integrate, we then need to define roughness lengths. So we have the same roughness lengths as before for momentum, but we also need to so-called also kind of roughness scales where temperature, when we integrate it, becomes, like in this case, it's a height where velocity becomes zero, but in case of temperature and water vapor, it's height where these values become equal to surface value. So some surface value, how you obtain surface value, that's another model that does this, because it should involve radiation, fluxes into the soil and other things. So you need to use some energy balance at the surface to obtain those fluxes, but we assume that, obtain those values, but we assume that we know those. So, and if you do this integration, you will come up, you come up with the following formulas, that u, h, so u is just velocity at the height h, and h, to remind you, it's our first grid level, so it should be placed somewhere within a surface layer. So generally h is something like maybe 10-20 meters. UH equals to U star divided by kappa, and it's defined, this function is defined such way that we have first formula for our neutral case and minus integral, and now we need to define eta. So this eta we defined as z over L, so that zh I mean not z. Actually it's z, yes. Is it z? No, it's eta, I think. So eta, or eta is different. Well, let's call it eta. Eta h equals to h over L, and eta 0 equals to z naught over L. So obviously we can easily go from z to eta by divided by L and multiplying by L. So instead of z we will have eta here. So we have some integral from eta 0 to eta h of some of this 1 minus f m of eta, and here it's d eta over eta not c. So we see that because we divide by z here when we at the right hand side, that's why we have this divided by this guy. So this function we call just let's call it psi m of the function of eta h eta 0, and we can obtain this analytically. This is analytical function, it's given, because again we assume that this function can be easily integrated analytically. So when we have neutral certification, this term will drop out and we have this just logarithmic profile. And similar, we can write that theta h minus theta at the surface equals to theta star divided by kappa logarithm z over z naught, let's call it T. So it's for temperature, Z naught for temperature, which is different than Z naught. So Z naught T is not equal to Z naught. So Z naught T is a height, hypothetical height, where temperature, potential temperature equals to surface temperature. And generally Z naught T is much smaller than Z naught. In fact, like much smaller, like maybe order of magnitude smaller from observations. And here we just write psi, but h of VH Z naught. And similar, I mean eta naught. And similar we can write it for QH minus QS. And now we, to obtain aerodynamic formulas, bulk aerodynamic formulas, we just basically substitute our definition of U star, because drag or momentum flux equal to U star square, and here we should multiply this guy by U star and do some algebra. So if we do that, we'll arrive to bulk aerodynamic formulas such that well, we wrote it already for momentum. So let's say that there are two components of momentum, U and V. So we will have that for this for U component, it's going to equal to with minus, because remember momentum flux is always negative. It's always going to the surface. That's why you need minus sign here to get it positive. It's C D drag coefficient times UH. And UH, it's actually its amplitude, so UH should be absolute value, and times UH. Well, this one should be capital U. Let's call it capital U. So capital U H equals to square root of U square plus V square. So this is just absolute value of wind. And this one is actual wind. It can be positive or negative. So when wind is actually blowing this direction, it will slow down. If it's this one, it will accelerate this direction, which is also slow down, right? So minus W prime V prime equals to CD, this again the same UH, times, so this is UH, so that value, times VH, and heat fluxes, which will be written as, say, for buoyancy flux, it's equal to CH UH times theta S minus theta H. So when the surface potential temperature is higher than temperature at height H, it's going to be positive, so heat flux is positive, it's going up. That's why it's defined. And similarly, I would write for water vapor, but you got the picture. So what's water vapor flux at this value at the surface? Well, over the ocean, obviously you assume that it's saturation value at temperature of the surface. But for land, it's much more difficult, different than that. It can be dry surface, can be slightly moist surface, and so on. We're not going to discuss it here, but so you need to use some other model that takes into account interaction with soil, moisture, and if you have vegetation, then also there is this process of evapotranspiration that you also need to take that into account, and that very complicated stuff. I'm not going to discuss it here. But generally, so basically you just need some other model to obtain those theta or NQ at the surface. So you have these guys, and this CD, CH, CD equals, we already wrote it, it's just kappa square divided by this log Z over Z naught minus this psi m, my psi m of theta h, function of two things, and theta 0, and this squared. And CH is actually a combination of two. It's effect of velocity and effect of temperature. So it's again log Z over Z naught T minus psi m of ZH Z naught times log Z over, no, here is Z naught, not T, but here is Z naught T minus psi H ZH Z naught. So you can compute your CD given this eta H and eta naught, and given and so basically now how to compute eta, you need to know L, and to know L you need to know flux of buoyancy, and you need to know U star, but U star is itself this left hand side. So in order to compute this guy, you need to know this guy. To compute this guy, you need to know this guy. To compute this guy, you need to know this guy. How you do it? So everything is kind of depends on itself. And of course, in this case, you use iterations. So you first assume some value of L. Let's say you assume that L is taken from previous time step. So you take L from previous time step. And then you compute, based on this L, you compute your eta. And you given theta S, it's those you know. UH you know, this you know. Let's say also from previous time steps, so they don't change. And then you just iterate, you compute your fluxes, and from that you compute your L, new L, And then you compute your new eta, you substitute in these formulas, you compute new CD and CH, you compute new fluxes, and you iterate it until your values don't change much. So you kind of converged. And that's basically what can be done, but it's kind of tedious process. So there is actually a better way of doing that, and I will share it with you right now. There is a way to do all this stuff without even knowing L, without even have to without having to actually know L or compute it. And for that, you can define so-called bulk Richardson number. So let's do it. So you probably remember what Richardson number is. It's basically a ratio of stability parameter, which is Brand-Weisshaller frequency, over shear, wind shear, vertical wind shear, let's say, in this case. So Richardson number is defined as its dimensionless number is G over theta. So it's our beta, right? Now it's d theta dz. So this is Brand-Weisshaller frequency squared divided by d, this capital H, or this, so it's total wind over dz squared. So this is Richardson number. So it's much of no use to us because there are these derivatives. So we replace with bulk number. So basically it's like linear representation of the vertical derivative by kind of using first order derivatives. So this would be called bulk B, Richardson B, bulk Richardson number, which is basically just this beta. This one is beta. So plus this beta. So beta, delta theta, and delta theta is just it's theta h minus theta s, and times h divided by u h square. So UH square is just delta U, but delta U equal to UH square. So this is a bulk Richardson number. And now we just basically what we do, we substitute our formulas. If we kind of have these terms in there, and so our bulk aerodynamic formulas we substitute in there. And if we do that, we actually arrive to the following expression, that this bulk Richardson number equals to eta h times this log of our z over z naught minus psi m eta h eta naught divided, so that was this h, sorry, divided by log z over z, so this one it should be then t, z naught minus psi m theta h, this one is t, theta h z eta naught squared. So this is now, so Richardson number can be computed from, it's our input. We know everything here, we can compute Richardson number right away, because you know this one is for from our model, it's first grid level. This one is from surface model, so we know surface value. This one we know from the grid. It's a velocity at the first level of the grid. This one is a height of the first level of the grid above the surface, and beta is just basically constant. And so this guy is known, and now this one, you see, this formula is only a function of eta. So you don't need actually L. You can iterate again, and for that you can use maybe your favorite method for solving nonlinear equation. That's one of our first lectures. But actually easy in this case just to use just simple iteration without actually like Newton method or something, because differentiating this function is pretty tedious. So just use a simple iteration so that you basically get your first value of eta as your first guess, let's say from previous time step, and you substitute in this thing, you compute these guys, and so basically you write that your eta equals to Richardson divided by all this formula, for example, and this one is your new plus one iteration. So anyway, so you solve this by your favorite iterative procedure. Actually, the interesting thing that for stable case, when you stable case, you don't even need to iterate, because you can, it actually produces quadratic equation that you can just solve analytically. But for unstable case, when heat flux is positive, unfortunately you need to iterate, because the equation cannot be solved analytically. So, but anyway, you can solve this, and as long as you found your eta, then you can substitute to your CD and CH expression that I wrote before. You find your bulk hydrodynamic formula coefficients, these bulk coefficients, and then you substitute into the bulk formula. You compute your fluxes, and then you use those fluxes in your model as your low boundary condition. So basically, that's all. Maybe a little comment. We always see these things here, like log z over z naught, and actually, if you have very tall obstacles, like for example forest, or very tall crops, or you have some suburban area with buildings and stuff, or just some urban area with a lot of tall buildings, this formula is very difficult to use, because your z naught can still be kind of relatively small. Like say for forest it can be say about 1 meter, but forests can be like, trees themselves can be like 10, 15 meters high. And actually this formula does not work okay, because the problem is that if you look at the flow, let's say that you have trees here, somewhere here, dense forest, and so this is your u, this is your z. Actually the velocity profile would look something like that. So it would look like this, and then beneath trees it would go like this. So see, it's definitely not anything like logarithm. So this theory does not really work for that case. So how to you account for that? You introduce so-called displacement height. So basically you say that, you know, this formula is basically applied to this height only, above the two canopy tops. So you need basically displace the whole thing up, and for that you just basically add another parameter. So instead of using z, so z naught is supplied. You use it from it's your data, input data. So people spend considerable amount of time to derive the z naught from observations. And so for given forest, let's say indigenous some forest, I don't know, some, I don't know, pine trees or something. you know z naught, and then displacement height is also your input parameter, and then in all formals instead of z you use z minus d. That's all. So that's just a little comment. And for little obstacles like maybe grass, for bare soil, for other kind of this kind of small obstacles, you don't need to do that because your well, here actually everywhere, of course, I need to use h, not z. So here it should be h minus d. So you just, but in all formulas you just, for small obstacles, d is very small, so it can be ignored. So you just use h over z naught. So only for very tall, for surface types that have tall obstacles, like a forest, for example, or say cornfield, which is very tall plants and stuff like that, you need to use displacement height in addition to roughness length. So but generally displacement height is parameterized in terms of obstacle height. Let's say 10% of obstacle height of displacement height, or 50%. It depends on your land type. So from this you see that it should be positive, so your h should be for sure higher than displacement height. So if your displacement height is 10 meters and your h is also 10 meters, Houston will have a problem here, right? So your h should be maybe 15 meters in that case to accommodate your forest underneath. So that's a little comment that I want to add. There are many other things that related to the surface parameterization that again involve vegetation, and that's very complicated issue, of course, and the whole, I don't know, half of the class can be taught just on various types of this, of treating vegetation in models. Usually we modelers don't design those, we treat them as a kind of black boxes. You can get this kind of models that computes vegetation, so it supplies you with all sorts of parameters that you want, like surface temperature, surface displacement height, maybe, and other things, and to use as a black box in your model. So you just download from somewhere, you provide, you create interface from your model, and you use it, because it would be very tedious process to develop it yourself from scratch, and you need to be actually expert in that area to develop actually comprehensive model of vegetation effect on surface fluxes. And similarly, radiation. Nobody codes their own radiation code to compute a transfer of radiation atmosphere. Those people who actually understand that stuff, they do it, and then you just use it in your model, providing some interface to that code. So that's why I'm not going to cover it, because it's basically vegetation is treatment of vegetation or vegetated surface is outside the scope of this class.